Watch a ball leave your hand, climb, and curve back down to the grass. You've seen it 1,000 times. That glowing arc is motion, and the story of how we pin it down with numbers goes further than you'd think. Start with the two simplest questions you could ask about the ball. How far is it gone, and how fast is it going? How far is just position. Where the ball is, measured from where it started, track it instant by instant, and you get a string of positions strung along its path. How fast is speed, the distance it covers each second. When those positions are evenly spaced, like beads on a wire, the ball is moving at a steady speed. Speed times time gives distance. A ball holding 10 meters per second for 3 seconds travels 30 meters. Simple bookkeeping of where and when. But speed alone leaves something out. Which way is the ball actually headed? Add direction to speed and you get velocity. 10 meters per second says little on its own. 10 meters per second up and to the right describes the throw. Velocity is a vector, a size and a heading together. Now look closely at the arc. Even if the ball's speed barely changes, its direction turns the whole way through the flight, so its velocity is changing every instant. That change in velocity each second is acceleration. Gravity is quietly supplying it, bending the velocity downward. Plot the flight and the motion speaks for itself. On a distance-time graph, a steeper line means a faster ball. On a velocity-time graph, a tilted line means the velocity is changing, and that tilt, that slope, is the acceleration laid bare. Push a little further, and that idea of a slope becomes a precise tool of its own. Shrink the gap between two measurements smaller and smaller, and the slope of the position graph at a single instant becomes the exact velocity right then. That is what velocity truly is. The rate position changes, written v equals dx by dt. Do it once more. The slope of the velocity graph is the acceleration. A equals dv by dt. Position, velocity, acceleration. Each one, the slope of the one before it. This is the calculus of motion, and it runs the whole arc. From a ball tossed across a field to the slope of a graph, one flight carried us the whole way. Position, then speed, then velocity with its direction, and the acceleration bending it back to Earth. Describe those, and you can describe the motion of anything.